a set of vectors v1 through vk is linearly independent let me put a little squiggly line under there if it's not linearly dependent. So note that this is equivalent to saying that the system C1 V1 plus dot 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 plus CK VK equals 0, where I'm solving for C1 through CK, has only the trivial solution. The trivial solution C1 equals dot 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 equals, actually let me move that over here, C1 equals dot 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 equals CK equals 0, and this is the same as theorem 2.6, or this is using theorem 2.6. Well, you can say, okay, how do we go about finding out whether a set of vectors is linearly independent, or equivalently, whether or not they're linearly dependent? Well, we can use row reduction. So use Gaussian elimination. So let's do an example. Are -1, 3, 2, 2, 1, 1, and 6, -4, -2 linearly independent? Equivalently, this is asking whether the system of equations, so does this system of equation C1 -1, 3, 2 plus C2 2, 1, 1 plus C3 6, -4, -2 equal 0 have only the trivial solution. Now I realized just now that I might not have said what trivial solution means. Trivial solution here, that means 0, the 0 solution. So the trivial solution is the same as saying 0. I guess mathematicians sometimes like having another word for things that are already having a word. So we want to know, does this have only the trivial solution? Is 0 the only solution? Well, we can check this using Gaussian elimination by putting these three things into the columns of a matrix and putting zeros on the right. So -1, 2, 6, 3, 1, -4, 2, 1, -2, 0, 0, 0, and then going and solving this, or using Gaussian elimination. I'll put G-E for Gaussian elimination until we get something that's in row echelon form. Here is what we get. And if we look at this, well, we have these two guys are our leading variables, which means that we have a free variable. So the number of free variables is 3. So that's the number of columns to the right of the vertical bar, or equivalently the number of variables, 1, 2, 3, minus 2 equals 1 is greater than 0. So therefore, there are infinitely many solutions, infinitely many solutions. And therefore, the answer is no. Those three vectors are not linearly independent. They are linearly dependent. So another example, and this is almost the same as the other example that we just did, the only difference being this 3 over here. Before, we had a -2 there, and now I have a 3. And I'm going to ask, is this linearly independent? And we can do the same procedure as we did in the last problem. We put these three guys into the columns of an augmented matrix, so -1, 2, 6, 3, 1, -4, 2, 1, 3, and put zeros to the right of the vertical bar. And then we use Gaussian elimination to put this into row echelon form, or reduced row echelon form if you prefer, but it's kind of overkill. So -1, 2, 6, 0, 0, 1, 2, 0, 0, 0, 1, 0. Whereas before, this 1 here was a 0. Now it's a 1. Okay, well, how many free variables? We have 1, 2, 3 leading variables, and so there are the number of free variables is equal to 3 minus 3 equals 0. So therefore there's only the trivial solution, and therefore indeed they are linearly independent. Sometimes one can very quickly see by inspection that a given set of vectors is linearly independent or linearly dependent. For instance, you can use a theorem. Okay, so if m is greater than n, then any set of m vectors in Rn is linearly dependent. So let's see why. The system where we put the m vectors as columns and augment with the 0 vector, like we did over here, for instance, well, that's a homogeneous system with m variables and n equations with m greater than n. And now all we need to do is use theorem 2.3 to say that we must have infinitely many solutions. And therefore, there's infinitely many coefficients that we can use to make something times the first guy plus something times the second guy plus something times the third guy plus dot 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 equal to 0. So there's infinitely many possible somethings there, and so therefore we get dependent. So a quick example of applying this theorem. We can look at 1, 2, 3, 4, and 5, 6, and know that those three vectors together must be linearly dependent. Because, well, there's 3 vectors and they live in R2.